Hi guys, I hope you're doing well. This is kind of a mini unit and it could have been attached onto the other unit, but I think it becomes really long if we did that. This unit, we're going to look at some algebra stuff, but also some graphical stuff, but there's definitely way less graphing than in the previous unit. So what we're going to look at here, let me just get rid of that, is kind of a theme in the course, which is to keep things as exact values, but also reduce them and simplify them. And I talked about that when we did simplifying radicals. Remember when we had the root of something and you could pull out a perfect square? We tried to reduce as much as possible, but also leave it as an exact value. This is in line in terms of that idea, where we simplify things and reduce them as much as possible. So the first thing, a rational expression. Rational just means that it's fractional. So you've got fractions. So in the past, you've always been asked to leave your answers in fractions, and that's exactly what we're going to do here, but you also need to reduce them. And then the expressions that we're going to have, because they have variables in them, this is going to be a bit new from what you've done in the past. So in the past, if we just dive in here and you look at the first example, it says simplify the following. So we're going to simplify part A. So you've done this many times, and hopefully you can kind of do this without even thinking about it or putting it into a calculator. But if you were to simplify this, what you would do, and you probably wouldn't write out all these steps, but you would look for a common factor to the numerator and the denominator. So what's a common factor that you can divide 18 by, but also divide 24 by? And so you look for the largest, common factor to those things. So if I did that, I could pull out a 6. So 6 times 3 is 18, and then 6 times 4 is 24. And again, you generally wouldn't write this step. You would just kind of cancel these things out. But that's actually what you're doing. You're pulling out the common factors so you can then divide them. And you end up with 3 over 4. And that's your simplified version of 18 over 24. They're equivalent, just simplified. Similarly, if you look at B, we look for common factors. And I'm not going to go through all the process of the steps. But if I was to look at this one, we're going to do a whole unit on exponent laws after this. But I would look at this and approach it as, what can I simplify the coefficients before I even look at the variables? So how can I simplify those coefficients? So I've got 150 divided by 100. So hopefully you see that you can just kind of divide both by 50. So that becomes 150 divided by 50 is 3. And then 100 divided by 50 is 2. So you know you're going to have 3 over 2 as part of your answer. The next part is to look at each variable separately. So one thing is, this is really x to the exponent 1 on top. So it's kind of like you've got, and if I write it out, it's like having x divided by x times x, because x times x is x squared. So if you were to divide these things, like this x would be divided by this x. So a common factor is x. And so it leaves just 1 on top and then an x in the denominator like that. So this really becomes 1 over x. And then you would move on to the y value, and you've got y cubed divided by y squared. And so in this case, y cubed divided by y squared, if you remember your exponent laws, rather than writing this all out with 3y's over 2y's, you would just simply subtract the exponents because you're dividing. So 3 minus 2 leaves 1, like that. And so that's the simplified expression to this original. So they're both equal to each other. It's just been simplified. In the next question, this is more like what we're going to be looking at. If we want to simplify this, we're going to follow the same idea. We're looking for a common factor to the top and bottom. But as it's written, there is no common factor because I can't simply just divide things like that. That doesn't make any sense. Because if I wrote something out equivalent, like let's say I had 3 plus 2 over 3 plus 4, and I said simplify that, you wouldn't just do this. You wouldn't say, oh, by 3. That would change the whole value of this. What you would have to do is simplify the numerator and then simplify the denominator, so this would become, I guess, 5 over 7. And so you can't just start canceling things out. It really doesn't make sense in math unless they're factors. And so it's really like all of the numerator divided by all of the denominator. And that's the conceptual understanding behind this. But what you need to do ultimately in order to find those factors is to literally factor it. So I'm going to factor that denominator. So this is why at the beginning of the course I said you really have to, have factoring. It just pops up all the time. You need to have that skill perfected. So when you look at the denominator, first thing is it's a simple trinomial because there's a 1 in front of the x squared. So these are the easier ones to factor. So I want two numbers that multiply to give negative 30 and add to give negative 1. And that means I can write them in this brackets like that. And so two numbers that multiply to give negative 30, hopefully you recognize, are going to be 6 and 5. And because it's negative 1 for my b value, it's going to be negative 6 and positive 5 like that. So now I have everything written in factors. And once I do that, now I can look at dividing what's common. And so if you look at it, obviously the x plus 5 divided by x plus 5 allows me to divide it. And what I'm left with is just a 1 on top, don't forget that, over x minus 6. And so this would be the simplified version of this expression. And so the key here is to always put things into factors. So that's one of the ideas that we're going to look at. And then there's a couple other things that go along with this. So one thing in math is that if we just scroll down a little bit, it says when you're simplifying rational expressions with variables in the denominator, we have to consider restricting values that make the denominator equal to 0. So for example, I can't have my denominator equal to 0 because let's say I just have something like this, 1 over x. I can't divide by 0, and we saw this in the last unit. If I have 1 over 0, this just gives me an error on my calculator, and the reason is because you can't divide by 0. It just doesn't make sense. And graphically, from this function, 1 over x, that creates an asymptote in this example. And so you have to state restrictions on your denominator. It's not hard, but you just have to recognize it. So in these examples, it says state the restrictions on the following functions. So the first one here, I put 1 over x minus 4. So as soon as I recognize there's a variable in the denominator, I have to think, okay, what would be my restriction? What's the thing that would make this denominator equal to 0? So, i.e., what would x equal to make it 0? So what I do is I take the denominator wherever x is, and I say x minus 4, and I say, rather than equal to 0, I say it can't be equal to 0. So it's very similar to what we were doing when we solved quadratics. So then I would move the 4 over, and so I end up with x cannot equal positive 4. And that makes sense. If I was to plug in 1 over 4 minus 4, that would become 1 over 0, which can't happen. And so this would be my restriction on this expression or this equation. So x cannot equal 4. If you look at b, this time, again, I've got an x here and also x in here. And so they're both factored, so we can just simply look at the restrictions. So you literally set it equal to 0, so x cannot equal 0, like that. So that's that restriction, that was easy. And then I do the same thing here. And then I try to solve for x, and so I end up with x cannot equal 1 over 2. And if I was to sub in 1 over 2 for x, you would find that that would make the denominator equal to 0. And so you don't have to think about the numerator because you're allowed to have 0 in the top, just not 0 in the bottom. So why don't you try the next one? So pause the video and see if you can get the restrictions for the denominator here. So if I do this, again, you're just setting this equal to 0, move the 1 over. So, oops. So x cannot equal 1 over 5, like that. And then similarly, and there's my two restrictions. So again, if you were to sub in those values into this equation, you would find that the denominators become 0. So it's not a complex idea, it's just something you have to remind yourself of whenever you have these situations where you're simplifying with variables in the denominator. So the other part of this is that, like I was talking about right at the beginning, is you really have, when you simplify things, you can have equivalent functions. And so equivalent functions are just that. It means that they're equal to each other. And so it's important to be able to recognize when you actually have, some expression that hasn't been simplified is equivalent to something that is simplified. And that means they're going to have basically all of the same features graphically and in terms of algebra. So if you look at this one, it says determine if f at x and g at x are equivalent. And so when I scan over this, so I've got f at x is this expression here, where I've got a bunch of stuff that can be multiplied through and then collect like terms. That's kind of an indicator that you can probably simplify it, and you may get it equivalent to this, which looks like it's been fully simplified. There's nothing left I can do there. So what I'm going to do I'm going to take f at x, and I'm just going to multiply things through. So I'll just repeat the equation like that, and then I'm going to simplify as much as I can. So remember here with the minus of the second binomial, the 3x minus 2, I have to put that negative into both of the terms. So I'm going to multiply this through, so that becomes 2x plus 2, and then minus 3x, and that becomes positive 2. And then if I collect my like terms, I get negative x plus 4. And it looks like there's nothing left I can do. So I compare this to g at x. G at x is written in the opposite order, but in fact, this is 4 minus x, the same thing. So f at x is equivalent to g at x. And so these are equivalent functions. So I'll say, therefore, f at x equals g at x. And if we were to look at these graphically, I'll just bring this up if I can. So here's the original. So the one that's not simplified, if it'll allow me. Maybe it's not going to. Oh, there we go. So that's that one. And if we looked at the other one, it's just overlaying it. They're the exact same graph as one would expect. So if I go back here, so now we've got something where we have a fraction for f at x. So if you look at it, and then g at x, same thing. So fractional or rational expressions. But the first one here, f at x, I can simplify this because it looks like the denominator can be factored. So I always have to have in mind, can I factor these things in order to try to see if they're equivalent? So I'm going to do just that. So I'm going to factor f at x. So my numerator is already factored. In my denominator, I'm going to factor that. And again, it's a simple trinomial. Remember, that's because the a value is 1. So that makes it a bit easier to factor. So I want two numbers that multiply to give negative 12 and add to give negative 1. And so if you work that out, this becomes, I guess, negative 4. So x minus 4 and x plus 3. So I get two factors there. So this is the step where I have to consider what my restrictions are on my variable. So if I look at the denominator only, before I divide the common factor, I have to state the restrictions. So what this means is that I can't have x cannot equal, so x cannot equal 4 from the first one, from the first brackets, and then also x cannot equal negative 3. So I have two values that x cannot equal. And I can write them like this, just side by side. X cannot equal 4, and then comma for the other one. If I had more, I would write more commas. After I do that, then I can divide the common factor. And so I end up with x plus 2 over x plus 3. So then if I look at g at x, which is the exact same thing, I know that these are going to be almost similar functions. The only difference here is that my restriction is, on this one, just x cannot be negative 3. So they're going to look almost the exact same. The only difference is that one has an extra restriction. And it's going to be a bit hard to see, but if you look at these, I'm just going to go back. So I'll get rid of those other ones we had. So these are going to be the graphs of, there's my original unsimplified, and here is my new one, which is the purple one. The only difference between these, so they look exactly the same, is that there's an additional restriction. We're going to talk about that. And the one we had was x cannot equal 4. And it's hard to see here. In fact, you could scroll in forever and never see it. But what happens right at 4, and you can see this here, it's undefined. And we'll talk about that in a second, but that's like what we would call is a hole in the graph. So technically, in this case, because the restrictions are not the same, f at x is not equivalent to g at x. And again, because the restrictions aren't the same. So a small difference are going to look very similar, except for this other one, the original, had this thing called a hole in the graph. Okay, let's look at this idea, the idea of a hole and the restrictions and what these restrictions represent. So if you look at the first one here, this is our graph that we had of 1 over x. And remember, for this, we get an asymptote at x equals 0. So if you think of the features of this reciprocal function, which we've talked about, or the rational function, there's an asymptote, which is x equals 0. And the reason is because I can't have 0, x cannot be 0, because that would make the denominator equal to 0. And so that's my restriction on this, restriction on this function is x cannot be equal to 0. Like that. And if you look at the next one, so you look at the equation, but also look at the graph. So if you look at the graph here, right at 3, I also have an asymptote. So my features here, I've got an asymptote at x equals 3. And if you look at the equation, and it's really important to relate these, if I subbed in a value of 3 for x, it would make the denominator equal to 0. So my restriction for this one is x cannot equal 3. And so you're seeing this relationship between the two, between the asymptote and what the restriction is, and that's important to note. So the next one's a bit different. Notice graphically, I've got just a straight line, and it's hard to see here, but there is actually a little circle here, and this is what represents a hole. And so normally you don't see it on the program Desmos, but on other programs it'll show you the hole there. What it means is that it's undefined, the function is undefined at that value for x. And so if we look at the equation, so the features here, I know there's a hole in my graph where it looks like it's the value for x of 1 and y is 2. So that's where the hole is. It's at 1, 2. Now, if you look at the equation, I've got x squared minus 1 divided by x minus 1. So even though there's an x squared, this graph is just a straight line. And if I wanted to simplify this thing, I can factor it. So I'm going to factor the numerator. And you might remember this is a special case where I have just two terms, a perfect square, which is x squared, minus another perfect square, which is 1. Whenever I have that, remember a squared minus b squared, it means I can factor it into a difference of squares where I have a minus b and a plus b. So this becomes square root of x squared is x, so x minus 1, square root of 1 is 1, and then x plus 1. So I can factor that into those two factors. So once I do that, now I can divide out what's common. And I'm going to divide out the thing in the denominator, x minus 1 on the numerator, and my restriction here is x cannot equal 1. And so you notice my restrictions match the whole. So my restriction here is x cannot equal 1. These two, right? It's the same one as the whole. And so this is what happens when you have a common factor to the numerator and the denominator. When it cancels out, when I divide these two common factors, it creates a whole. So anything that is a common factor, when it divides out, it creates a whole. Versus here, if I go back to the first two examples, nothing divided here, it created an asymptote. And that's what's going to happen. So let's just look at a couple more examples to show that point. So the next one, I've got x minus 1 divided by x minus 1. It's already all the work's done for us. But I can simplify this by dividing it. And remember, when I divide it, anything over itself is just 1. So this becomes 1 over 1, or just 1. And so I get this straight line of y equals 1. So this is my graph, y equals 1. And again, hard to see, but there is a little hole here at x equals 1. And if I was to look at the y value, it looks like 1 as well. And so my features, I've got a hole at 1, 1. And then my restriction, if I go back to my algebra, to the equation, this, I could not have x equal to positive 1. So x cannot equal 1. And again, anything that divides out is going to be a whole. And the next one's an interesting one because it has both. And so this is kind of leading into advanced functions, but it's still relevant to what we're doing. So on the numerator, I've got x plus 1, and the denominator I also have x plus 1. So if I state my restrictions here, x cannot equal negative 1, but also x cannot equal 3. So if I look graphically, I've got an asymptote at 3, but a whole at negative 1. And the reason is because when I do this, x plus 1 divided by x plus 1, there's a 1 up top, but that's what creates the whole. So I've got a whole at x equals negative 1, and then the x minus 3 remains, and so that's my asymptote, which is x equals 3. So I've got two features here. I've got an asymptote, which is x equals 3, and then a whole at, and this is kind of hard to see and I'm not too worried. I'm just going to write actually the x equals, I don't care about the y value so much, you're not going to have to worry about that. X equals negative 1. So that's my whole, that was the thing that divided out in the equation. And then my restrictions will match those two. And so x cannot equal negative 1 and positive 3. So I get two restrictions. So just some ideas to match up to what we're doing when we simplify, but also to what it's creating graphically and why we have to state those restrictions. So just to summarize, two things happen if you divide by 0. You get either an asymptote or a whole. That's always going to be the case. The behavior of the function can only be found if we simplify it down, i.e. we have to factor and then divide. So some parts of the function or expression cancel each other out. This results in a whole. So that's when we divide the common factor. And then once the function is completely simplified after we've divided everything that we can, and there's still a value for x that cannot equal 0, that results in an asymptote. So just exactly what we were doing right there. Okay, so that's kind of the background on this stuff. Now we're going to get into the algebra, and we're going to do a few days of stuff like this, but this is kind of the basis of it. And so when you're simplifying rational expressions, the first thing you always have to try to do is to factor. If you do not factor, you're ultimately not doing this properly. And sometimes you'll see you don't have to factor because it's already in a factored form. But if you don't, then you start to cancel things. It just doesn't make sense mathematically. And the next thing, right after you factor, we state the restrictions. Again, it's only from the denominator. And then the next thing is to do whatever. You multiply, divide, you do your operations. So we simplify. And if you want to think of it, it's canceling out. I like to just say divide rather than cancel. Okay, let's try a few here, and then I'm going to get you to try some. So the first one here, just like what we were trying up above, only now we're also going to state restrictions. So right off the start, there's only, just to reiterate, there is only one term in the numerator and only one term in the denominator. Everything's being multiplied or divided. And so we don't have to factor here. You can't factor. There's not more terms than one. And so the first thing we should do is state what the restrictions are. So in this case, before I divide, I'm going to say, look at the denominator, and what would make this denominator equal to 0? Well, one thing, I've got two different variables. So because it's 15 times a times b, the only thing that would make this 0 is if I multiplied by 0. And so a, therefore, cannot equal 0, and b cannot equal 0. And those are my restrictions. So I state those, and then I'm done with them. The next step is to just do the operations like I stated above, where we simplify. So again, just deal with the coefficient first and then move on. So 20 over 15 can be simplified by dividing both by 5. So this becomes 4 over 3. Done. Then look at the next variable. So your first variable is a. So I get a squared divided by a. That becomes just a on top. So I subtract the exponents, which is 2 minus 1. And then notice the b divided by b just becomes 1. And so I have no b. So this is my final simplified answer, which is 4 over 3a. And we keep our restrictions just as they were. So the next one, recognize here I've got 2 terms on top and 3 terms on bottom with adding and subtracting in between. So what that tells me is I have to factor. So the top, the numerator here, I've got x squared minus 4x, and there's only 2 terms. Anytime you're factoring, if you go back and think about when we factored, the first thing you should do is look for a common factor. So what's common to x squared and 4x? And the answer would be x. So I take x out. So I end up with x left minus 4. So again, it's like I divided both terms by x. So that's factored into the numerator, and then I factor the denominator. Notice it's a trinomial. I've got an a value of 1 in front of x squared, so I want 2 numbers that multiply to give negative 4 and also add to give negative 3. So I know it's going to factor into something like this. So if the answer here would be minus 4 and positive 1. So once I've got that all factored, I have to state my restrictions. So I only look at the denominator. So x cannot equal 4 and x cannot equal negative 1. I don't worry about the numerator, I don't have to. After I've done that, then you can divide what's common. And so you end up with x over x plus 1. And in this question, it doesn't state, determine what the asymptotes are or the wholes. And so we just leave it. We don't have to do anything about that. That was just to show you, some of the background here. Then, so as long as we've canceled everything out that we can, we're done. You cannot cancel out the x with the x plus 1 because remember, it's like there's brackets in the denominator. If you don't have the same thing in a bracket in the top and the bottom, then you can't divide it out. Okay, next one is also I need to factor. And so I'm going to start here. I've got y minus x, so I'm going to leave that for now. And then in the denominator, I've got x squared minus y squared. So again, this is a difference of squares because I have perfect square minus another perfect square. So I can factor it into x minus y times x plus y, like that. And so at this point, I can state my restrictions. So x cannot, this one's a bit tricky, maybe I'll take a couple steps. Because I've got both x and y within their brackets, what I need to do is I take x minus y cannot equal 0, and then I move the y over, x cannot equal y. And so they can't be equal to each other. I do the same thing with the other bracket, so x plus y cannot equal 0, so x cannot equal negative y. So they can't be equal to each other or the negative version of each other. So there's my 2 restrictions. Now I look to see if I can divide what's common to the top and bottom. It looks really close. I've got positive y here minus x. And then in the denominator, though, in the first bracket, I've got positive x but negative y. What I can do here is I can factor a negative from the numerator. So I'm going to factor a negative. So if I do that, it's like I pull out a negative or I multiply by a negative, whichever you'd prefer, which changes the sign of both y and negative x. So I end up with positive x minus y like that. Now it's going to match what's in the denominator. So sometimes when you get this situation where they look really similar, but there's a sign that's preventing you from doing it, you can just simply factor a negative. Now I can divide the common factor. So in the numerator, I'm left with, this becomes negative 1. Remember, you always have to leave a 1. And then in the denominator, I have x plus y. And we're done. So negative over x plus y. So you can do the you try down here, and I'll put in the answers. You can check your answers on the OneNote general sheet and see how you do. Okay, if you have any questions, of course, let me